So today we're working on part 2 of applications of equations, and again our objective here is to solve application problems. So in the last video you saw me work through the first 4 problems, and now we're going to pick up on the 5th problem. And this time we have a canoeist that paddled a total of 11 hours on a 48-kilometer round trip to Bear Lake. The upstream trip to Bear Lake followed by a period of heavy rain, and the current he paddled against was 3 kilometers per hour. And then for the downstream return trip, he paddled with the current that slowed him to 2 kilometers per hour. At what speed could he paddle in the canoe in still water? So what happens is when he's going upstream, then he's paddling against a current that's slowing his speed down, his speed in still water down by that 3 kilometers, and then on the way back it's sort of helping him. So the way I would set this one up to get started is, or let's review something really quick first. There's a formula that's going to help us here, and it's distance is equal to rate times time. Basic formula we've known for a while. Now, keeping that in mind, what I would do is go ahead and organize this information in a chart. Okay, and in the first column, what I would do is I would label this distance. And then I would label this rate. And then I would label this time. And then I would come over here to the other side. And I would label one of the rows going upstream, one down. And then I would give myself a total. Now let's think about putting this stuff in and what we know about it. Okay, the distance. He's going upstream, turn around, and coming back. So what we know is that these two right here are the same. So that's something to keep in mind. Okay, those two distances, upstream and downstream, are going to be equal. Okay, as for the rate, what's going to happen is we're gonna have to define a variable, and we're going to come over here and say let r, or you might be more comfortable saying x. Either way. X is going to be exactly what we're looking for, which is the still water, okay? Okay, so we're going to keep that. So his rate going upstream is going to be a little bit slower than that. And how much slower? Well, it was coming down at this 3 kilometers per hour, what he was paddling against. Now going the other direction, it was helping him out, but it had changed slightly because the rainstorm had sort of calmed down by that time. Now when we talk about the time, what it tells us is that the total time was 11 hours. So this is 11, we know that. And then we need to fill in a little more information in order to be able to work this out. So we're going to think about another version of this here. And let's see, we have a 48 kilometers. So since this is the same, the distance, we know we were going 24 and 24, right? Now, to fill in that time slot, what we're going to do is think about another version of this formula, which is that time would be equal to the distance divided by the rate. And if that's the case, then we can say that this time here is going to be the distance, which is 24, divided by the rate going upstream, which is x minus 3. And then for the second one, going downstream, we could say that it is again the distance, which is 24, divided by the rate, and this time it's x plus 2. And now that we have that chart set up, it's going to be pretty easy. Keep in mind that the distances are equal here, and keep in mind that you want to use the information on your chart. And if you notice here, we have everything filled in this column. So what that means to us is that if we add those two times up, then we should get 11, and that's really going to be our equation. So you've got the 24 over the x minus 3 plus the 24 over the x plus 2 is going to be equal to 11. Now once we have that, it's just a matter of getting this equation in a form that we can work with and graph. So we have a denominator of x minus 3 and x plus 2, which is a little bit problematic. So what I'm going to do is get rid of those denominators by multiplying the entire equation by x minus 3 times x plus 2. So when I do that, I'm going to get the x minus 3's would cancel out on that first term, and you get 24 times x plus 2 plus 24, and now in the second term, the x plus 2's are going to cancel out. X minus 3 is equal to 11 times x minus 3 times x plus 2. Okay, so it looks better, but still a little bit complicated. So I would go ahead and go through and multiply this stuff out and see if we could simplify things. So it's just going to be a process. Here we get 24x plus 48 plus 24x minus 72 is equal to, and now here we need to multiply this entire, first you want to FOIL the x minus 3 times x plus 2 and then distribute the 11. When you do all of that, you're going to get 11x squared minus 11x minus 66. Okay, now from here we're just going to get everything on one side of our equation just by combining like terms and all of that, and we end up with 0 is equal to 11x squared minus 59x minus 42. Now this would be a good time to pause the video and make sure that you could get from this step to this step by taking care of your algebra. Okay, so once we're there, it's factoring. We could also use a calculator, find our x-intercepts. We could use a quadratic formula. In this case, it does factor, so that's what I'm going to do. I'm going to factor it. It's going to factor as 11x plus 7 times x minus 6. Right? So now that I have that, that means that it's going to produce two solutions. If I set this first one equal to 0, 11x plus 7 equals 0, then I would get x is equal to negative 7 over 11. Or the other possibility is going to be x minus 6 equals 0, so that means x is equal to 6. Now you have to think about what you know. It's going to be, this is the speed in still water. So what we know then is that it's not going to be a negative speed in still water. So the rate in still water is going to be 6 kilometers per hour. Okay, and that's the solution to that problem. Okay, moving on to the next problem. This time we have a walkway of uniform width. It's going to be built around a square swimming pool with 18-foot edges, and we're looking to find out how wide the walkway should be to make the area of the walkway surface 400 square feet. All right, so here we have the pool. Okay, and then in red we're going to have this walkway. And the area that we want to be 400 square feet is here in red. Okay? And it's a uniform walkway. So what that means to us is that if I look at this right here, then that's going to be x, and that's going to be x. So it's a uniform walkway here. We know that the dimensions of the pool are, it has 18-foot edges, so it's square. So that's 18 by 18. Okay. So given that information, then all we need to do is really just write an equation for this. So what we have is you have the, one way to think about this is you have this big piece here with a, you could say all of it, but what we want to do is not all of this is going to be the walkway because you have the pool inside there. So what we have to do is subtract out the pool area. Okay, so we need to think about the dimensions. Well, if the dimensions of the pool are 18 and the width here is x, so you can see that if this is 18 and then we're adding to it x on both sides, then the dimensions of the bigger are going to be 18 plus 2x. And this is going to be 18 plus 2x. And the 2x is coming because if you think about the pool in here, you're getting x here, that's x, and then you're getting x there, the length, adding both of those to the original 18 of the pool. All right, so that means that we have 18 plus 2x is going to be the area on the outside, but now we need to knock out that pool area, which is going to be 18 squared, 18 by 18 pool. And what we want to happen is for that to be 400. All right. So now that's our equation. So it's the area, the exterior area, minus the pool area is equal to the 400 square feet that we wanted in our problem. Okay. And so now we're going to use our calculator to solve that just by finding the intersection. You should go ahead and plug that in your calculator. It'd be a good time to pause the video and see if you could come up with it by yourself. Okay, so I'm going to turn this off. And my equations were here and here, and I'm finding the intersection. Now, again, you have to think about the dimensions of the pool. You know, started out as 18 by 18, so you know that, you know, for a pool, you're not going to be super huge. So I'm going to use a window for my x's from -25, which I probably don't even need to do the negative part of that, up to 25. Okay? And I'm going to use a scale of 5. And then for my y values, we're talking about square footage. Well, we talked about a 400 square foot area, so I'm going to go a little bit above that. And I'm going to do -10. We're not going to have a negative area, so not much there. And then I'm taking this up to 500, and I'll do a scale of 100. And let's look at a graph there. And we do see an intersection, okay? So we see a intersection at a negative point here, which is not going to be useful to us. Let's see. All right. Get my screen back. All right, here's my picture that I want to look at. Okay, so this is the graph you get here. This right here is going to be when x is something negative. Okay, we're not going to have a negative dimension. So the one that we're really looking at as a solution is this guy. And if you do your second calc intersect on your calculator, then you should be able to find that. So second calc intersect is number 5. Yes, that's the first curve. So I'm going to get a little bit closer so it finds the right one. Yep. It's asking me for the second, yes, and yes, I want it to guess. And that gives me an intersection of approximately 4.45. So if we come over here, then x is approximately 4.45. That is going to be that's what we're looking for there, because it asks us how wide should the walkway be to make the area's walkway surface area 400 square feet. So the answer is that it should be about 4.45 feet. Okay. All right. Number 7. We've got a container in the shape of a regular prism with no top. It's going to have a volume, and it's going to be constructed from a 28 by 20 piece of sheet metal. And we're going to cut square edges out, and they're going to be equal size from each of the corners, folding the flaps up. And that's how we're going to create our rectangular prism. And what we want to know is what size the squares that we cut out from the corner should be in order to make that happen. Okay, so we've got this piece of metal here. And what we're going to do is we're going to cut these edges out. All right. And then we're going to fold up the flaps. And once we fold up those flaps, we will have our rectangular prism that it's talking about here. Now, it tells us that we have, this is 28 initially, and this is 20. Now, once we make some changes to this and cut this out, so let's say this is x, this would be x, and the same thing all the way around, okay? All right. So we have those x's. So what that means is if we're taking x off of this here, so the length that we're actually talking about here is no longer 20. It's just this way is here in green. So that means we need to take away the 2x's that we took off. So this is 20 minus 2x now, and this is going to be 28 minus 2x. All right. So what you'll have is a piece that's 20 minus 2x by 28 minus 2x by x, which x would be the height of it because you're going to fold those flaps up. And we want it to have a volume of, and it didn't say that, so I left this out on accident, but the volume should be 650 cubic meters. All right. So now we have enough information to write our equation. So it's length times width times height, so that's going to give us x times 20 minus 2x times the 28 minus 2x. And that's going to be equal to 650. And at this point, we can just plug it into the calculator like this and find the intersections. Let's do that. Okay, here we're going to turn that one on and this one on. Okay, now graph. It's not going to show us anything to begin with, probably because we don't have a very good scaler. Actually, it does show us a little bit. We're looking for the intersection. Now, the intersection, we're looking for where the y value is going to hit 650. Okay, so that should give us a little bit of a clue about what to do here. And our x value is going to be positive, but certainly no more than 20 because we can't take 20 off of. It actually can't be more than 10 because if we're cutting that amount out of each side, then we can't go more than halfway, or we can't even go halfway. There would be no side. So let's go to our window, and we're going to take this from -5 up to 20, which is way too much. We can should only make that 10. And then we can do a scale of 5 is fine. And then our minimum at -10, that's fine. It's going up to 650. So we need to go, maybe we'll go to 750 here. So we can see. Okay. And then our, actually put that in the wrong spot, -10. And we can leave that at 100. That's fine. Let's see on the graph now. All right, so we do have a couple of solutions there, and let's go through and find those. Second calc, we're looking for the intersection, which is number 5. I'm going to go to the far left and find the one on the left first. There it comes. Okay. All right, press enter. That's the first one. Second one. Yes, we want it to guess. So the first one is x is about 1.54. So one possibility is x is approximately 1.54. All right, let's try it again. And again, we're looking for the intersection. Should see it soon. You can change your viewing window if you wanted to be able to see that a little better. Second curve, yes, guess. And the second one is approximately 6.68. Okay. And then let's find the last one, second calc. Again, the intersection. There it comes. Okay. Press enter, enter, and yes, guess. And we get 15.78. Okay, so those are our possibilities here, and of those we could cut out 1.4 0.54 from each of those because it started out as 20. That's fine. We could cut out 6.68 from both of those. Then that would leave still something here in the middle. That would be fine. But we can't cut 15 out here and 15 out here because the whole thing to begin with was only 20. So this is not a possibility. So your two possibilities are that it could be 1.54 inches or 6.68 inches, okay? And those are your two solutions here. All right, one problem left, and in this one we've got a chemist who has a 30 milliliter solution of 40% acid in a test tube. How much of the solution should be poured off and replaced with pure acid so that the new mixture is 70% acid? Okay, so what happens is that we have this container, and it's got in it some 40% solution, okay, 40% acid. All right, and it's not full because we poured some of it off, and we don't want it to be 40% acid anymore. We want it to be 70%. That's our goal, is to get it at 70% acid. And so it makes sense that we have to add 100% acid to it to bring that level up to 70% acid. Okay, so what we're looking for is how much 100% acid do we have to add to that. Okay, so let's say that to start out with, what we have here is X milliliters here in this container, or here in the 40% section. Now, we know that the whole thing together is 30 milliliters. All right? So if that's X milliliters there at the 40%, then how much was this up here that we poured off to come up with this 70% solution? Well, the answer is that it's going to be the 30 minus what we have in the bottom of the container, which is red, because together they have to add up. And if you do 30 minus X plus X, then you get the 30, which checks out. All right, now we need to put that together in an equation. What we want is for the percentage to be 70%. Okay, we want the percentage to be 70%. So you have to think, how do you come up with a percentage? Well, it's part over whole is all it is. So we get part over the whole. The whole part is 30 milliliters. You know that. The part that is going to be 30%, or the part that's going to be acid, is the 100% acid piece, which is going to be 1. If you change 100% to a decimal, you get 1. All right? So it's 1 times the 30 minus X. All of that is acid. Okay? Plus, in the red area, only 40% of that is acid. So 40% of what's in the X area is acid. So you've got 100% acid here and 40% acid here divided by the total, which should give us 70%. So that's how we set up that equation. And now if we just simplify this, then we're going to end up with 30 minus 0.6x is equal to 21. All right, and continue to simplify that. We get negative 0.6x is equal to negative 9. And then X is going to be 15 milliliters. So we need to pour off 15 milliliters and add back 15 milliliters of 100% acid so that we have a 70% acid solution there. And that's all I have for section 2.3.